class today. We have a class on Friday, by which time I hope to finish most of what is required for electronic spectroscopy. From Monday onwards, we will move on to magnetic resonance, essentially Riemann effect, and the optical Riemann effect. Banwell already treats by now, but I have not done it. But when you do NMR, I have to tell you this is exactly what happens. The molecules in the optical region, and you see there's a big parallel between the NMR experiments that you learn, which you already have seen actually, and the optical Riemann effect, which is one and the same thing, excepting that the transitions occur at two different frequencies. But the science behind them is absolutely identical. So we will look at that a little later. So from next week, we will look at NMR and ESR, and if time permits, we will look at X-ray spectroscopy towards the end. But we will certainly look at NMR and ESR in the process. I missed one class, I need to make that up, but we will make it up next week. So this week is rather tough. There's too many things to do. So we will have the extra class sometime on Wednesday or thereabouts next week and make up for that. I hope that's audible right here, right? Okay. As usual, before we start, Nikhil and Vishnu. And Nikhil. Almost looks like celebrating his birthday. Okay. Today I think it is the birthday of Sabatier. Sabatier reaction, I'm sure you have studied in chemistry. It is essentially fixing carbon dioxide in the presence of a catalyst to produce methane, and that is an extremely important reaction because it essentially tries to produce fuel out of carbon dioxide. And Sabatier was born today, was essentially responsible for having discovered that reaction. For tomorrow, 7th, is a real big day. The reason being is Curie's birthday. It's C.V. Raman's birthday. That's the reason why we're celebrating the chemistry week during this week. Because these two are really great personalities. I mean, you must really read the biography of Curie. Absolutely inspiring. For somebody to be so dedicated and committed to what one is doing, I think the best example is probably Marie Curie. So Curie is 7, C.V. Raman is 7, and a person who should have got Nobel Prize but didn't get it, because these are right now. And she was also born on November 7. There are certain days when if you're born, you go to the Nobel Prize site and look at and just collecting birthdays and see where that birthdays sort of pile up. There are certain days where you have a large number of Nobel Prize winners on that day. So I think if you're born that day, then we have some hope. So 7 is in fact one possibility. So we already have 2 Nobel laureates on that. The other one is, any of you born on February 28th? I believe 28th February actually has the largest number of Nobel Prize winners born on that. I think it's like 6 or 7. And Pauling is one of them. Linus Pauling is one of them. So anyway, happy birthday to both of you. In absentia 1 and in presence 1. And we will get on to what we were doing the last time around. We were looking at pre-dissociation. And when I say pre-dissociation, when I talk about pre-dissociation, I'm basically talking about dissociating a molecule when I have not given it enough energy to actually dissociate. Because if I take the molecule in a ground electronic state, and now we know what I mean by an electronic transition, when I keep saying I have made an electronic transition, I have actually transported the molecule from one potential curve to another, and in that process, I have sort of tampered with the electron configuration. It's gone from one orbital to the other. And once you do that, you change the potential under which the molecule actually has to vibrate and rotate. So when I do this, I'm actually going from here to here, and we saw all the other associated complications. What are the vibration selection rules? What are the rotation selection rules? No problem with the rotation. It's still delta J equals plus minus 1. Mostly, you can have 0 also. But I've been avoiding such situations as of now. But when it came to vibrations, It's not the simple harmonic oscillator selection rule that you are aware of, which was applicable for transitions happening within that potential. In a jumping potential, going from one to the other, that rule is no longer valid. We expanded the transition probability intervals, we collected a few of them, we in fact used the Born-Oppenheimer approximation, and finally we came up with the conclusion that what is important for us is the overlap integral of the vibrational wave function in the ground state and in the upper state. So the vibration wave function downstairs and the vibration wave function upstairs, to what extent they overlap actually decides how strong your transitions will be. And we call that as the Frank-Quantum principle, first initiated by Frank in a certain way, but had its drawbacks, not quantitative, seemed to be violating the principles of quantum mechanics. But then when quantum gave the wave mechanical form of formalism, things seem to be in place. We are essentially looking at the quantity psi e prime, psi e double prime, eta, and actually the square of this is what we call as the Frank quantum factor. It's essentially probability stuff. So if we have one, then I know that particular transition is using up all the probability you possibly can have. Or if it's like 0.9, then I know there's 10% of transition that must be elsewhere. We go looking for that. But then we said if I go from here to here, I'm actually putting the molecule from one well into another well, and it will still keep oscillating within this well. It won't dissociate. What will it do at best? It will sit there for a while, and then it will jump back. And when it jumps back, again the Frank quantum principle will tell you where I must go. If I start from here, where do I end? If I start from here, where do I end on top? So whether it's absorption or an emission process, the Frank quantum principle or the Frank quantum factors actually decide for you what the intensities of these various transitions are going to be. But then we said, if I put a molecule up here and leave it here, instead of buying bound potential, it really should not dissociate. Anywhere up here. However, we saw that situation, a very weird situation, in which perhaps a curve that sort of crosses the first potential, but the curve that crosses is actually a repulsive potential or a dissociated potential. So when I jump from here to here, and if but for this curve, the molecule would still be vibrating in there without getting dissociated, and eventually after a certain period of time, it will jump back, still intact. So it's a diatomic to begin with, diatomic to end up with, back to the original state, still it's a diatomic. It has not split into atoms. However, if it is a curve crossing like this, then we said what can happen is points such as these, which if you look under the Frank's formalism, what does that mean? A molecule at this point on this potential curve has complete potential energy and no kinetic energy. A molecule on this potential curve at this point also has complete potential energy and no kinetic energy, and therefore it can make a jump at that point and not violating the internuclear distance rule and not violating the kinetic energy rule. The Frank's formula. In the quantum formula, what would that mean? It would simply mean a huge overlap of the vibration wave function of this state and the vibration wave function, or the wave function corresponding to this energy. You ask me what is the vibration wave function over there? There's a wave by which you will calculate those wave functions, which we will not worry about. But at that point in energy, you can calculate a wave function. And that wave function for this state and this wave function for this state will have a huge overlap at this point, which essentially means that the molecule can jump from here, it vibrates back and forth, but at some point it could jump on this potential and then find its way out. If the potential was not there, it can't happen. And therefore we say the molecule have actually dissociated ahead of time. It's dissociated even though it has not been given the energy required for dissociation. What is the energy required for dissociation in this state? I will really go from here all the way up to here. Only then I can dissociate. However, I'm only going part ways up and still ending up breaking that molecule into two. And that is essentially happening because of the intervention of this dissociative state. And we call this phenomenon as pre-dissociation. What about this vibration? If I excite the molecule to this vibration level, but it can't. Because at this point, you see this has got potential energy. But at this point on this potential, it's got some potential plus kinetic. In other words, in continuous formalism, the wave function overlap will be rather small. And therefore, you will find that at the point where the curve crosses is the place where you're going to have the most crossover from one state to the other, from a bound state to a dissociated state. And when that happens, the molecule essentially breaks into two. So there are the weird situations. I excite from here to here, molecule is intact. Here, intact. Here, breaks. Back, intact. Which means below the crossing, the molecule is intact. Above the crossing, the molecule is intact. But somewhere in between, the molecule is gone. Of course, it's not so dramatic. I made it look like nothing happens. This state, nothing happens, and that one state it dissociates. No, it doesn't happen that way. Nothing happens, tends to dissociate a little, but there's some overlap. Very strong dissociation, a little bit of dissociation, no dissociation, and then finally, of course, you have normal dissociation. So when you look at the vibrational pattern, you see strong lines and then a diffuse one. Why is it diffuse? Molecules are breaking apart. And back again, you see a strong vibration progression. So the progression will not be continuous in the sense you will not see 0, 0, 0, 1, 0, 2, 0, 3, and so on. You will see 0, 0, 0, 1, 0, 2. 0, 3 might actually be missing, and you will have a smear out there. The 0, 4, 0, 5 might again come back. And anytime this happens, you must watch out. You probably are looking at the possibility of a predissociation. Of course, in real life, it's not as simple. There are many other reasons why it can happen. But as far as this particular argument is concerned, we know one thing. That if you see some such phenomena where there's an unusual loss of intensity, then you need to watch out because there could be a possibility of the molecule dissociating ahead of time, which is predissociation. Okay. And that's extremely important in spectroscopy because there are quite a few situations where this happens, and you then have a spectrum that really looks out of the ordinary. But every time the spectrum looks out of the ordinary, then you know you have something very interesting to look at, such as field. What I will do now is, before we go on to anything else, we'll start looking at some phenomena which we have avoided so far, and that is something called line broadening. Because this is related to this. This is not there in Banwell. It's there in Wallace. It's there in a few of those. But I'm going to treat it in a very elementary way. So you should be able to find enough material on the internet or on a book like Wallace, which is pretty good for spectroscopy. But I'm going to treat it in a rather elementary way, just to give you a feel for what spectral line shapes will really look like when you record a spectrum. You have recorded the spectrum of the infrared bands. You have recorded the spectrum of fluorescence. You have recorded UV visible spectra. And tell me in any one case where you had a spectrum that looked like, no, you'll never get this. Even though that is what you should be getting. Why? What am I really doing? I'm going from one level to the other level. So if I go from this level to this level, there will be one energy. This energy is quantized. This energy is quantized. And therefore, this is fixed. And therefore, in any transition, when I'm jumping from one level to another, I must really get just one sharp line. But I don't think you've ever seen a sharp line so far in any of the spectral experiments that you have done. It's always something like this, or in infrared, you got something like this. It's broad. The broadening or the width of the spectral line is actually trying to tell us a whole lot of things with regard to the dynamics of the process. And what do we mean by that? When I say that I'm making a transition from here to here, what is eventually fixed by that statement? The energy required to make this jump, that is fixed. So if I say that this state is 20,000 wave numbers above this, then I know if I shine 20,000 wave number light, the molecule will actually make a transition and jump from the lower state to the upper state. So I must get something at 20,000 wave numbers. So where this line will appear is actually going to be determined by the energy level differences. That's it. But having fixed that, having decided that I must have a line at 20,000 wave numbers, we really go back and try to look at that line. As I said, it's not going to look like a sharp line. There is a width to that. And when there is a width to that, that width is essentially telling me a whole lot about the dynamics of the whole process that's going on in that system. Today what we will try to do is to see whether we can unravel some of that processing that's sort of going on during the absorption process. Or in other words, the question we are asking ourselves is, why are those lines broad? They have no business to be broad, because if the two levels are fixed, I must have a sharp line. Very rare. If you really want a sharp line, you must do the experiments that we sort of do. We go to great lengths to get those lines to sharpen up. We take the molecule, we cool them down to 10 Kelvin, we trap them in gas, and after doing all of that, we get the lines down to be extremely sharp. But if you don't do that, the lines by themselves are going to be rather broad. The reason why they are broad, there are quite a few reasons, and we will go through a few of them, the important ones, as to why these are broad. The first reason why that is broad has to do with Professor Heisenberg. And why am I bringing this guy? The biggest energy level, let's say it's the ground state. If I say it's the ground state, well, that's the lowest energy possible. You put a molecule in there, it will just stay there forever. So here's my X state, and let's say this is an A state. If it is molecule, if it is an atom, then of course you have to label it by triplet P, singlet O1, singlet S or whatever. Let's say this is the state X, this is state A ground state, and an excited state. If I shine light and get the molecule up here, the molecule will stay there. But is it going to stay there forever? No. Because systems are forever trying to reach their lowest energy states. A natural phenomenon.